Have you ever stopped to actually think about the everyday miracle of just lifting something heavy? Whether you're picking up a loaded barbell at the gym or literally just carrying your groceries into the house, the biological machinery required to make that happen is absolutely staggering. Welcome to this explainer. Today we're going to take a journey descending deep into the human body. We're going to start all the way up at the level of the bones and whole muscles that you can actually see and feel, and we'll travel all the way down to a microscopic world of proteins and molecules that essentially act like tiny biological engines. So let's dive right into this.
Here's our roadmap for this explainer. First, the human skeleton. Second, muscle macrostructure, before we shrink down to muscle microstructure. Fourth, the sliding filament theory. And finally, the phases of contraction.
All right, part one, the human skeleton, the foundation.
Okay, before we can even talk about how muscles move, we have to establish what they're actually moving, right? Because muscles can only pull, they literally cannot push, they desperately need a system of solid levers. Right at the center of our 206-bone foundation is the axial skeleton. That's your skull, your vertebral column, ribs, and sternum. And attached to that is the appendicular skeleton, which is your shoulder girdle, your pelvis, and the bones of your arms and legs. When your muscles contract, they're pulling against these bony levers, rotating them around your joints so you can push or pull against the world around you.
And honestly, this brilliantly illustrates why your workouts matter far beyond just building muscle. If you subject this skeleton to heavy loads, or if you perform explosive movements with high-impact landings, the bone will actually adapt. The axial skeleton, when it's loaded frequently and intensely, responds by increasing its density and bone mineral content. So you are literally forging a stronger foundation every single time you train.
Moving right along to section 2, muscle macrostructure, layers of strength.
Now we're peeling back that first biological layer, transitioning from hard bone to soft tissue. A cross-section of skeletal muscle looks exactly like a Russian nesting doll. It isn't just one solid slab of meat, it's a highly organized organ containing connective tissue, nerves, and blood vessels. You've got an outer layer surrounding the whole muscle, which contains bundles of fibers, which in turn contain individual fibers. It's layers within layers within layers, and it's all designed to channel force into one unified direction. But the really crucial point here is how this muscle actually grips the bone. The outermost layer of that Russian nesting doll is called the epimysium. It covers our skeletal muscles and seamlessly blends right into the tendons at the ends of the muscle. Those tendons are then attached directly to the bone periosteum. Because of this continuous, unbroken chain, any internal contraction deep inside the muscle pulls directly on the tendon and in turn pulls the bone.
All right, section 3, muscle microstructure, the cellular level.
We are zooming in much closer now, shrinking down to individual muscle cells known as muscle fibers. At the critical intersection where your nervous system actually meets the muscular system, we find the motor unit. A motor neuron branches out from the spinal cord and connects to the muscle fiber at what's called the neuromuscular junction. And it's amazing, a single motor neuron can innervate hundreds or sometimes even thousands of muscle fibers at once. When that neuron fires, all the fibers it's connected to activate and develop force together. And if you look inside just one of those single muscle fibers, you'll find it completely packed with specialized organelles. Inside that muscle fiber cytoplasm, which we call the sarcoplasm, are hundreds of myofibrils. Let's just pause for a second to wrap our heads around the scale here, just to remind ourselves exactly how tiny we've gotten. A single myofibril is about 1/100th the diameter of a human hair. No way, right? And yet, hundreds of these microscopic threads totally dominate the inside of the muscle cell, holding the actual physical apparatus that makes your muscles contract. Which brings us to section 4, the sliding filament theory, molecular movement.
Okay, we're tackling the heavy science now, zooming past the cellular level all the way down to the actual molecular proteins. Those myofibrils we just talked about, they're divided into tiny segments called sarcomeres. The sarcomere is the absolute smallest contractile unit of skeletal muscle. To put this in perspective, they average just 2.5 micrometers in length. We are talking about approximately 4,500 of these sarcomeres packed into just a single centimeter of muscle length, and their specific arrangement is actually what gives skeletal muscle that alternating dark and light striped pattern.
Inside the sarcomere, you've got two main types of protein filaments, the thick filaments, which are called myosin, and the thin filaments, called actin. Notice how the thick myosin filaments have these little globular heads poking out from them. Those heads form what we call cross bridges, and they literally reach out and physically attach themselves to the thin actin filaments. Movement actually happens when these actin filaments are pulled inward by the myosin heads.
Let me tell you exactly why this matters for you. There's a fundamental rule here.
The number of cross bridges that are formed between actin and myosin at any given instant in time perfectly dictates the force production of a muscle. So that raw physical strength you feel doing a heavy deadlift or a massive push-up, it's not magic. It is mathematically tied directly to the total number of these tiny molecular bridges successfully grabbing hold and pulling at that exact millisecond. All right, final section. Section 5, the phases of contraction, action at the micro level.
We're going to really speed up the pacing here, because this is a rapid, action-oriented sequence of biochemistry that happens literally in the blink of an eye. To make this engine run, you need two crucial things: calcium and ATP. When your brain sends that electrical action potential zipping down the motor neuron, it triggers the release of stored calcium inside the muscle fiber. This calcium binds to a protein on the actin filament, exposing the binding site so the myosin head can attach. Meanwhile, ATP, adenosine triphosphate, is broken down to provide the explosive energy you need for the actual pulling action.
Let's rapidly walk through this 5-step mechanical cycle. 1. Initiation. ATP splits, energizing the myosin head. 2. Phosphate release. The myosin head changes shape and locks onto the exposed actin. 3. The power stroke. The myosin violently pulls the actin filament toward the center of the sarcomere. 4. Detachment. A brand new ATP molecule arrives, forcing the myosin head to let go and detach from the actin. And 5. Reset. The head is re-energized and ready to grab the next site. Attach, pull, detach, reset. It fires exactly like a cylinder in a car engine.
I really want to emphasize step 3, the power stroke. Because a single power stroke only moves the actin a microscopic, invisible distance. Measurable human movement actually requires rapid, repeated flexions across millions of cross bridges simultaneously. As the actin is pulled toward the center, the entire sarcomere shrinks. Specifically, an area called the H zone gets smaller. Multiply that microscopic shrinking by millions, and suddenly, boom, your bicep curls the weight.
So, think about what we've covered. We've traveled from the 206 whole bones of your skeleton through the dense layers of the epimysium, down to the nerve cell, and finally straight into the rapid-fire chemical engine of actin and myosin. Next time you lift a weight, I really want you to ask yourself, how many millions of microscopic power strokes fueled by nothing but calcium and ATP are happening right now just to move that bar? It is an immense, invisible biological machinery operating inside you every single second. Thanks so much for joining me for this explainer, and keep marveling at the mechanics of your own movement.